pure substance is when you have particles that are of one kind. Now, this is a very vague statement. I haven't described what particles are. I haven't described what we mean by kind, but it is deliberately left to be so because there's a lot of room for explanation here. Similarly, impure substances are the ones that have particles of different kind. So let's try to explain this. What do I mean by particle? A particle is small enough part of matter that can act on its own. So an atom is a particle. So a particle is a general term, and an atom would be a particle because an atom can act on its own, it can remain on its own. But then the question comes up, why not a proton? Why isn't that a particle? Or why not an electron on its own? Isn't that a particle? Thing is, it is, but an electron on its own won't make a substance. A proton on its own won't make a substance. Substance is basically what we call element, compound, and mixture. So the thing is, you can't have atom or anything smaller than atom as a particle because it cannot make a substance. So electron on its own, while it's a subatomic particle. So there we enter into the world of subatomic particle, and there we have neutrons, we have electrons, and we have protons, and I'll talk about them later today. So that's what we have over there, but they cannot make substances. But what atoms can do is that they can make substances. That is why we say that particles are atoms. Similarly, then we have ions. And we'll talk about what ions are. And then the third level of particle is molecule. So this molecule, this ion, this atom, these three are the small things that make the universe. And substances are the large things that make the universe, and they are all made of these particles. So two of these are pure. I'm going to highlight those. So these in blue, element and compound, they are pure. So I'm going to highlight it like that. And impure is this thing in green, that is a mixture. So a mixture is impure kind, which obviously we know that it is particles of different kind. What does that mean? It means that it can have atoms, it can have ions, it can have molecules, it can be a combination of those, it can be different kinds of atoms, but it has to be a combination of those. But what do I mean by combination? It is possible that we can say atom is a combination of neutron, electron, and proton, right? So how come that combination doesn't make it a mixture? So the thing is, there are two types of combinations. One is chemical and one is physical. So this chemical composition, chemical mixing together, chemical combination is different from physical combination. How so? Usually we say that chemical combination is when there is a transaction involved. An electron is transferred, an electron is shared. There has to be something to do with the electron for a chemical combination to occur. But in physical combination, that doesn't happen. So at the heart of it, some involvement. So this is brought about by involvement of electrons. And physical combination doesn't involve that. So while that does explain it, like, does that explain what a chemical combination is and how it is different from physical combination? There has to be an involvement of electron for things to be chemically combined. Okay, so that means that there are many different ways in which physical combinations differ from chemical combination. For example, first of all, chemical combination will mean a new substance is created. So new substances formed. And in fact, this is a pure substance that is made out of chemical combination. In physical combination, no new pure substances are made. Okay. Physical combination, on the other hand, has its own advantages because there is no hardcore interaction. The physical combination is easy to reverse. When I say easy, that means that there is a small amount of energy that we need to do that. And when I say that they are difficult to reverse, then that means that you need to supply a large amount or a name for that energy. If you want to reverse or you want to do any chemical interaction or chemical combination, we call that delta H. That is the enthalpy change that you have to supply, that you have to do for any chemical combination to come about. But in physical processes, we don't really need that much energy. And we usually don't even quantify that, unless, of course, it is in physics where they're concerned with those things. So, physical combination is easily reversible. Chemical combination is quite difficult to reverse. Again, this is comparative. I'm not saying that they're not reversible. All combinations are reversible. Remember that. Okay. Then this is easily separable as well. So how do we reverse it or how we separate them? The physically combined things. We have different techniques to do that. So for example, filtration is a technique that we use to separate things that are physically combined. Chromatography is a technique. And we will talk about these in detail. So chromatography, filtration, uh, distillation. There are two kinds of distillation in your syllabus. These are both easily reversible. There isn't much electricity required to do that. There isn't much amount of energy that you need to reverse these. But when it comes to chemical combination, the bill is quite high. So I'll quickly list them all down. So we also have decanting or centrifuging as processes to separate these things. Now, these are fairly easy to do. They don't require a lot of energy. But when it comes to chemical combination and how do we reverse them, then there is a redox method to reverse them. There is an electrolysis method to reverse chemical change. There is decomposition method, which is usually through uh, heat or light, which we call photochemical. So there is a decomposition required. For example, you have calcium carbonate, you heat it, it will break down and become calcium oxide and carbon dioxide. Totally new substance is made. Similarly, you have silver chloride, you give it lots of sunlight, it will break down and form silver and chlorine gas. Photochemical decomposition reaction. And that is why we call them. These are all reactions. We have a whole new name for them. For physical combination, we don't really have that. We don't even need that. The requirements are really low. So for chemical composition, you sometimes need modern equipment, you need a lot of energy to do that, you need specific gear to do that. In physical combination, things are relatively easier and quite basic. So does that explain how chemical combination is different from physical combination? Now, we can use this idea of physical combination being easy to do to test different things. So we can test things through physical methods and we can test things through chemical methods. So there are physical tests and chemical tests all around. So for example, if I want to check physical test for purity, I want to check if something is pure and I just want to have a physical test for it. Then what will I do? I will boil it or I will freeze it. And if it is a pure thing, it will freeze or boil at fixed temperature. And we have already talked about why there's a fixed temperature. That is a fixed temperature because that is when all the intermolecular forces are being overcome or created. And because These are pure substances which are all made of same kind of particle. The forces that they have are also same as each other, which is why you just need a fixed temperature to achieve that. So let's suppose I want to check if something I have, a colorless liquid, is that a pure water or not? So I will simply freeze it. If it freezes at exactly zero, then that is pure. If it boils at exactly 100, then it is pure. So that is a test which is physical test for purity. So that's an example. Water freezes at 0 degrees Celsius or 100 degrees Celsius is when it boils. Another test is that it gives one spot on chromatogram. Now, what does that mean? That simply means that when you try to separate it through physical methods, the filtration, chromatography, distillation, decanting methods, you only end up with one thing at the end because it's a pure substance. So all physical processes will not be able to separate it. All right. So pure substances are impossible to separate or break down using physical methods. All right. Now let's look at chemical composition or chemical tests. So chemical tests usually involve some reaction. So for every particle, they will be different. So usually reactions are involved. So reactions specific to that. So it's not that you cannot find out what reactions there are. So for example, in the case of water, there is a test. That is a chemical test. So the test would be that you take, for water, you have two tests. There is copper 2 chloride paper. So I will write it as copper's chloride formula, or we can write it as its name. So copper 2 chloride paper goes blue, blue. So that is a test for what happens. So this is blue in the beginning, and then it converts to pink color. On the other hand, if you have copper anhydrous copper sulfate, so this is anhydrous. Anhydrous means that it doesn't have water in it. So anhydrous copper 2 sulfate powder is white. But when you add water to it, it goes and becomes blue. So that is again basically a chemical test because a chemical combination has occurred. A new substance has created, which is pink in color for copper 2 chloride and which is blue in color for copper 2 sulfate. It's a totally new substance. It behaves totally differently. Similarly, we can have these tests all the time. For example, if I want to check for metal. So if I want to check if something is a metal, then a physical test would be to conduct electricity, right? And if I want to check if it is a metal and I want to do a chemical test, then I will probably have to test it with an acid to react it. So metals can have physical tests, which are easy to do, that they conduct electricity. But for chemical tests, we will need to react them. And again, there are some exceptions over there. Some acids don't react with metals. Some metals don't react with acids. Similarly, I'll give another example of acids. If I want to check if something is an acid, then I can have a physical test. So for acids, I can have a physical test of checking whether it's a pure acid or not. I simply react it with litmus paper or any indicator that I have. It goes from blue to red. But if I want to check it for, let's suppose, a chemical test for acid, then I have so many different ways of doing that. I can react it with metal to get hydrogen gas. I can react it with a carbonate salt to get carbon dioxide. I can react it with an alkali to get a salt, which is a neutral salt. The pH will change. So all these kind of tests we can run on it to check if it is a pure substance or not. And not just that it's a pure substance, we can also check which substance it is. We can even identify that thing without having to look at individual particles. And there's a whole chapter dedicated to knowing just that thing. What is that thing made of? So, for example, in the case of salts, we can check what salt it is by testing it with simple compounds like sodium hydroxide. That's a chemical test for checking. Sometimes it gives white precipitate, sometimes it gives red precipitate, sometimes it gives blue precipitates. And those precipitates, those colors are chemical tests for checking what that thing is. So all of this is basically to show what that substance is. So there's a whole science, there's a whole branch of chemistry which is qualitative analysis, which is just concerned with finding out what that thing is. So they use very sophisticated machines. In fact, it's such a booming business that, for example, we want to check if something is indeed coronavirus. Then what do? We go to a company that has acquired the required technology to check it. And what do? They have these chemical tests that they run. They cannot do physical tests because coronavirus is really, really small. So what do? They do these chemical tests on it, which is PCR. And through that, they find out that indeed this thing is coronavirus. And it's a big business. And not just that, it requires a lot of people coming together, working together to achieve that technology. And it's all just a chemical test for knowing what virus it is. The lab tests that we do, there is a big lab on Firozpur Road by government of Pakistan. That is the whole job of that is just to find out every new medicine that comes into the market. Is it what they claim it to be? It's just that. So there's a whole science, there's a whole branch, there's a whole field that is just dedicated to finding out, number one, if something is pure, and number two, if it is what it says on it. So that begs the question, why is it so important to us? And the reason is that there is a huge cost. There's a lot of things that are at stake when it comes to purity. That can be a financial cost, that can be a cost of life, that can be a cost of value, intellectual property, all of that. For example, medicine is a whole field where purity is very, very important, because you can't give an impure medicine to somebody and expect it to give the results that we require. Similarly, food is a quantity that we want to be pure. We want it to be exactly what we expect it to be. So if you're buying milk, you want it to be milk. You don't want it to be something that has white chemicals in it that are mixed together. Although that might look like milk, it might not be. Similarly, there are fields where cost is important. Like if you're buying jewelry, then you are going to spend your hard-earned money on it. You don't want to be fooled and buying something that is impure. So we have these different tests, physical tests usually, or even chemical tests if the cost is really high, to check whether something is, let's suppose, pure gold or not, or 24, 28, or 22 karat gold or not, or if something is platinum. Why? Because there is cost and risk. So knowing how to know if something is pure and getting pure things, it's important. And we can do these physical tests for it. So chromatography, distillation, decanting, filtration, we can do all of that to check if something is pure and to check what kind of substances are in it. These are low cost methods usually, not always, but usually. And sometimes we need to do chemical tests. So some chemical tests that we study in O levels are redox, electrolysis, qualitative analysis, decomposition. So that all of that has to do with whether it is pure substance or not. Can you think of a field or an industry where we need these methods to check or to separate pure substances? So everybody, give me an example. So crude oil is indeed separated into different useful fractions, because you see, on its own, crude oil is pretty useless. But once you separate it into different things, can you name a few of those fractions? We call them fractions. So these are all different fractions that we get by distillation of crude oil. Okay, some other industry that you can think of where we need or run these things. to separate stuff or to get new substances. Do you know that there are four metals for which uh, there's a region in Africa that is rich in those four metals? And there has been a war going on for over 20 years to control those mines. All four of them are used to make phones and laptops. So it's a big business. And why is that? Because when you get those minerals, you have to do electrolysis or you have to do redox to separate them and to make pure metals, which are then used to make these devices. This is the drinking water industry will require physical processes to separate water in separate pure water, drinkable water, and to make use of it. Yeah, you're right. So you see that we have different kinds of substances and we need different methods to separate them. And there are two kinds of methods, chemical and physical. Chemical combination can only be reversed through chemical methods, which are redox, electrolysis, decomposition, and many others. And physical combination can only be reversed through physical methods, and those are filtration, chromatography, distillation. These three are very important when it comes to O-level syllabus, but there are others as well. One key thing that is different for chemical combination and physical combination is that in chemical combination, there's always a pure new substance that is created. And in physical combination, no new pure substance is created. We can have pure physical tests for checking for purity. So something, if boiling or freezing or changing its state at fixed temperature, that means that it is pure. And it must also give a single spot on chromatogram. And for chemical tests, we have these reactions that are specific to that. And some reaction that we need to memorize are that water will will show these two color changes. With copper 2 chloride paper, it converts it from blue to pink. And anhydrous copper 2 sulfate goes from white to blue when it comes to water. Then there are many different industries where purity is important. So medicine and food being the foremost. And similarly, there are many different industries that make use of these separation techniques. So crude oil industry, water purification industry, uh, uh, fractional distillation of air is also an active field of industry where we need to get nitrogen to make fertilizer from the air. Similarly, oxygen to supply to uh, aircrafts or to hospitals. So we get that from the air again. So all of that depends on perfecting these chemical techniques. All right, so let's look at what do we get when we separate them. So element and compound is pure, as I said. So why exactly are there two pure substances? The reason is that elements are all made of only one kind of atoms. And compounds are all made of only one kind of these ions or molecules. True, there are some elements that are made of ions. So then that means that for elements, we can have one kind of atoms or one kind of molecules. And for compounds, we will have one kind of ions or one kind of molecules. So I'll give you some examples. For example, can you tell me a pure element and what particle is it made of? Alina, can you name any one element and tell me what kind of particle is it made of?
I'm sorry, sir. Can you repeat the whole question?
My question is, if I'm talking about elements, then can you give an example of a pure element and what kind of particle it is made of?
Any element?
Yeah, sure.
Carbon
Okay.
is an element.
So what kind of particle is it made of?
It's made of carbon atoms.
Good. Carbon is a very interesting example because even though it is pure, it comes out in 5 or 6 different shapes. There is diamond, there is graphite, there is graphene, there is CNTs, there is uh, fullerenes, a whole family of fullerenes. So carbon is a very interesting example. It's an element that comes out in many different shapes. And we have a name for that. We call those things allotropes. So same element, but coming out in different structures. So these are different structures of same element. So carbon is an example that it has graphite, diamond, and fullerenes. Can you think of any other element that exhibits this property allotrop? It's very useful, important for life, by the way, that element. It is indeed the oxygen. Yes. Does anybody know what allotropes of oxygen are there?
Oxygen and ozone.
Very good. So there's oxygen gas and there is ozone. And they're both different allotropes. This is O2 and this is O3. They're both the same element. Now, some compounds do something like this as well. Same compound, but showing up as different structure. So those are called isomers if they're organic. So compounds with same formula and molecular formula basically, but different structure. And this is true for only organic compounds. Crystalline compounds, ionic compounds, they don't show these different shapes. Molecular compounds will do though. So isomers, an example of that would be that you can have, so you can have carbon attached like this with chlorine, or carbon attached like this with chlorine. These are isomers. The placement of these chlorine atoms makes them different isomers. And we will look at these shapes and how do these molecules come around and all that. So yeah, Amna, your example is absolutely right. So alcohols show this. So as you've mentioned, propanol, you can have this thing. So this is a compound. Just because the placement of oxygen atom is different, the compound starts to behave different. It has different properties, different boiling point, different melting point. Everything is different for it, just because the placement of atoms has been different. So this is isomers. Just like elements show allotropes, these compounds show isomers. So that's the thing. All elements are made from the same kind of atoms. Sometimes they're made from same kind of molecules. So oxygen, chlorine, bromine, iodine, acetylene, all the group 7, nitrogen, hydrogen, they all exist as diatomic molecules. But some elements, these are all elements that exist as diatomic molecules. But most elements exist as just simple atoms. So noble gases, all of them, or metals, all of them. They are individual atoms that are combined together, making a whole substance. Mixtures, on the other hand, are made from these different types of molecules or ions or atoms. So some common mixtures that we rely on. Can you give an example of a mixture that we usually rely on?
Air.
Air, water, then sand. We use it all the time. Salt, we use it all the time to show how we can separate them. Ink. These are some mixtures that we rely on to separate stuff. But why exactly do we pick these examples? These substances are not important. What's important is what they show. So alcohol. Why? Because mixtures are categorized based on their behavior. So water is selected because it's a very common solvent. Sand is selected because it's a very insoluble thing and common insoluble thing. Table salt is selected because it's a soluble thing. Alcohol is selected because it is a miscible thing. Ink because it is made from miscible particles. Air, again, because it's made from miscible particles or miscible substances. And all the examples that we see when it comes to separation or separation techniques, they're all based on these. Why? It is not important to know whether we are able to separate water and sand, but it is very important to know if we can separate insoluble things from the solvent that they're part of. So I need you to look at the methods that we'll study. Obviously, you have to consider water as an example of a solvent. It doesn't have to be water, just water. If I remove it and I say, okay, now we're going to do filtration with some ketone, that shouldn't bother you. That because you have learned the technique for separating a solvent. Similarly, if I say that I'm able to filter sand and make residue, I'm saying these words, but I'll explain what they are. That does not mean that I am very interested in finding out how to separate sand. Basically, I'm interested as a student of chemistry, I'm interested in separating insoluble things from these solvents. So remember that all these examples that we use in the lab, no scientist is obsessed with separating sand or salt, which is a very common example, and people have been doing it since grade 7, I think. But we are obsessed with separating soluble and insoluble things. And that is where we'll start our next lesson. That how do you separate these uh, different groups of mixtures, and how do you make new substances from them? Okay. So now we are going to do a worksheet that will be on substances, elements, compounds, mixtures, and hopefully things will be more clear to you that what they are and how do we separate them. So here's a test that I used. This is about the topic that we studied yesterday, and some of it is related to what we studied today. So go ahead. According to kinetic particle theory, how does a gas expand? By the way, when it comes to these MCQs, sometimes you don't even need to look at the options. You can explain, you can give the answer right away. So for example, kinetic molecular theory, how does a gas expand? It expands because particles go further away. The particles are further apart. That's it. And we say that their volume has increased. Yeah. The answer is D, yes. Which term describes the process by which particles escape from the surface of a non-boiling liquid and enter the gaseous state? This is evaporation. And we will talk about evaporation. Uh, Basically, evaporation is when high energy particles, so when we study energetics, which is enthalpy changes, we will talk about how evaporation actually happens. How do particles in a solid behave? So particles in a solid, do they move or do they not move? We have a specific word for it. They vibrate. That was in your notes as well. So we say that these vibrate about their fixed position. So the answer here is C. Okay. What causes the high density of solids? So let's try to understand what density means. Density means that particles are packed together. That's what density is. So because high density means that they're packed together much more closely. So why is that? That is because solid have particles that are really, really close together. And because of that, you have, even in a very small volume, you have many particles packed in. So the answer again is C. At pressures greater than 1 atmospheric pressure, water will boil at. So how does pressure affect boiling? Again, uh, if you have higher pressure, then what you're doing is you're pushing the liquid down. So that means that this liquid is going to need more energy to evaporate or to boil because there is a greater force from the top. So because of that, at pressure greater than 1 atm, which is basically room pressure, water will boil at a temperature higher than 100 degrees Celsius. Why? How does water counter this extra pressure? By having higher kinetic energy. So the answer is A. Good. I see that Alina and Amna are sending me answers. You guys should also start working like this. A gas in a container of fixed volume is heated. So let's try to make sense of what it's saying. It's a fixed volume container. That means the volume will not change. So obviously the other two things will, the pressure and the temperature. What happens to the molecule of the gas? So we are heating it, so temperature is changing. So as temperature increases, they gain more kinetic energy. So that means they move faster. And not only do they move faster, they start to collide more and they will hit each other. So according to the options that we have, very good, Iman, the answer would be C. All right, which diagram represents the change in arrangement of molecules in a solid? So let's see what's happening here. We have a solid that we need to start with, and we have to make a liquid. Now, the difference in solid and liquid is that in solids, particles are packed together in definite order, and in liquids, they are separated and there are greater distances, sorry. Very good, Mishal, and very good, Noor. The answer is indeed A. Okay. In a liquid, some energetic molecules break free from the surface even when the liquid is too cold for bubbles to form. Wait a minute. What is it trying to do? It sounds like a cryptic message, but the basic thing that they're saying is it's not boiling. Because you see, when do bubbles form? When things boil. So in a liquid, some energetic molecules break free. Okay. So high energy particles are leaving from the surface When the liquid is too cold for bubbles, they are talking about evaporation, right? So many things here. Some energetic molecules are breaking free only from the surface, and there's no boiling, there's no bubbles. So yeah, this is evaporation. Good, good. A piston is supported by gas trapped in a cylinder. So this diagram, they use it all the time. What is it? This is an inverted syringe, nothing else. Although I've seen it in cartoons as well. It explodes. But never mind. A piston is supported by gas trapped in a cylinder. A weight is put on the piston. The volume of the gas supporting the piston decreases. So basically, what they're doing is they're pushing it down, so the volume is decreased. The temperature is unchanged. What does that mean? It means that kinetic energy does not change for this. So, what happens to the molecules? Obviously, you're decreasing their volume and you're not allowing them to move more. So, they are going to come close together, and there's pressure that will be increased, right? Remember, this is a tricky question. D cannot be the answer, although our first attempt would be, oh, this is D. They are coming closer together, they'll move faster. But the thing is that temperature is unchanged. So yeah, very good, Noor, Mishal, and Amna. The answer is A. They hit the piston more frequently, which is another way of saying that there's higher pressure. Okay, what happens to the molecules of a gas when the gas changes into a liquid? Pretty simple. This is a fact that we need to remember, that when they become gas, the molecules themselves stay the same size. It's just that they go further away and they gain energy. Similarly, when they become a liquid, as the question is requiring us to answer, they will move closer together and they will lose energy. So the answer here is A. Good, Iman. So the answer is A. Use the kinetic particle theory to explain why evaporation has a cooling effect. Very important conceptual question. Uh, who will answer it? Take a shot at it. You might have to speak, I think, because.
Can I?
Sure, go ahead, Michelle.
When evaporation takes place, the high energy particles in the substance to break free from the entire substance and escape into the atmosphere, which is why it loses kinetic energy in the which is essentially temperature. And as the energy is lost, the particles start to the substance cools down.
Good. Now, a couple of things we would like to change there. First of all, because high energy particles are leaving, the average kinetic energy, so the word average is important. The average kinetic energy will reduce, so they will have a lower average energy. So Hani has explained it. Hani says that the particles with a high energy break free, decreasing the average kinetic energy. Very good. So once the average kinetic energy comes down, the second point is for mentioning that how is that related to temperature. So we'll simply say that the average kinetic energy represents temperature. So at lower value, obviously the temperature is lower. Good. Amna's answer is also perfect. It says that high energetic particles break and leave the surface, leaving behind less energetic particles. You just have to mention how that is related to temperature. Okay, so one point is saying that high energy particles are leaving, and the second point is for saying that now we have lower average kinetic energy, which is lower temperature. Okay, explain why gases are easier to compress than liquids. Now remember, you have to get hints from kinetic particle theory for this, and you have to mention those words like particle, you have to mention forces, you have to mention distances. Those key points, if you mention those, it will be easier for you to explain and easier to score marks. Okay, so
So gases are easier to compress because they have larger distances between the particles and the forces of attraction are low.
good. But do we need to mention forces of attraction? Turns out we don't. We'll just say, as you started off, that they have large distances between them, which we can easily reduce compared to liquids. We don't have that large distances. So one thing you have to consider when you're answering questions like this, where there is a comparison involved, you have to talk about both the things that are being compared. So right now the comparison was between gases and liquids. So when you're answering this in the exam, talk about gases as well as liquids. So you can, a way to explain this would be that gas particles have larger distances between them than liquids. So there's a sense of comparison. So it is easier to bring them close together than liquids. Okay, temperature of a boiling pure liquid does not change. So energy is used to break the bonds, so no change in temperature. I would like to change the word here. Instead of saying bonds, I will say forces. So energy is used to break the forces, so no change in temperature. Good. I think this is perfect. It answers the question perfectly. Rate of evaporation is slower at low temperature. Okay, so I'll answer it. First of all, what is rate? Rate is something happening per unit time. Okay, so that means evaporation, the amount or the volume of liquid evaporating is less per unit time if you have low temperature. So let me talk about evaporation now. So evaporation is when high energy particles leave. Okay, low temperature means that they already have very little energy. So the particles have low kinetic energy. Mishal has answered this, that particles have low kinetic energy, so they're slow to break through the surface of the liquid. We'll just add a few terms here and the answer will be perfect. We'll say less particles have high energy. Because you see, it's low temperature, they already have low kinetic energy. So very few particles have high enough energy to leave. Okay. So if the average is, let's suppose, 5, then very few particles could be at 100. But if the average is 50, then a higher number of particles might be at 100, right? So we'll say that less number of particles, because you see, this is rate of evaporation, number of particles going to a gaseous state per unit time. So we'll talk about that. We'll say that less number of particles have higher energy, which is why the rate of evaporation is slow. Impurities lower the melting point. Actually, this has been taken out of the syllabus, so I won't answer it. Just remember that impurities lower the boiling point, lower the melting point, raise the boiling point. Reasons for this are no longer in the syllabus. Okay. Can anybody just look at these two values, and tell me, what do these values tell us about purity of the thing being melted? So it says that a cube of ice changes to water. What does this value tell me? In particular, this value. What does this tell me about this experiment being done?
It's an impure substance.
Answer is that it's an anomaly, which is correct, because you see, you can't expect such a large distance. A student is measuring the temperature. They see it's -1, then they see it's -1 again, but suddenly it's rising to 3. That's not how temperature changes. So certainly this student is performing the experiment badly. Same for this, I would say. Because you see, these values are -1 being repeated multiple times. Why is the value? So this is my second question. Why is this value repeating so many times? So let's see what it represents. It's basically telling me that even though time is passing, the temperature is still the same. And obviously, if the temperature is the same, that means a change in state is happening. If the temperature is the same, then state is changing. If the temperature was changing, kinetic energy would change. So right now, energy is being used to break forces. We won't say temperature is being used to break forces. We'll say energy is being used to break forces. So the reason it is constant, the temperature, it is because the substance is changing its state. Now, can anybody tell me what does the value being -1 tell me about the composition of this thing, of water, especially about purity of water? So I'll repeat. The question is, what does the value -1 tell me about purity of water? Yes, Amna. Very good. It basically tells me that this is impure. Pure water would would freeze or melt at 0. This one is doing it at -1, so this is definitely an impure sample. Okay, next question. Why is this value the same? Very good, Sophia. it says that the mass remains the same at different temperature. That is perfect because it is a physical change. The state is changing. Obviously, mass will not change at all. Now, what happens to the particles as this process occurs? Like we are heating it up, but the temperature is not changing. What is happening to the particles? So whenever a question like this comes, you have to talk about the main ideas in kinetic particle theory: kinetic energy, forces, distances. So right now, from this to this, over here, temperature is increasing, which means kinetic energy is increasing. Over here, from this to this, kinetic energy is not increasing. It's not changing. And over here, kinetic energy is increasing again. So there are three parts of this table, and particles are behaving differently in all of them. When the temperature is changing, particles are moving faster. When the temperature is not changing, particles are overcoming the forces between them. Energy is being used over there. Okay. All right. Thank you.